Hi everyone. So in this video, I'm going to very briefly just be talking about a very specific mechanism for a reaction between an epoxide and a Grignard reaction. And I'm going to talk about the nucleophile and the electrophile, the curved arrow mechanism, the overall electron flow, and then also just the regiochemistry and stereochemistry, and talk about how the molecule may end up oriented or what preferences the molecules may have during the reaction with regards to their stereochemistry. So firstly, just to talk about the reaction specifically. So this reaction is the reaction between an epoxide, which we see right here. It's a ringed structure with an oxygen atom attached to another chain, and a Grignard reactant. Basically just has that magnesium bromide group attached to it. So the structure of this reaction is that the epoxide is added to or reacts with the Grignard molecule and then undergoes a neutralization reaction or an H3O plus workup to result with this structure right here, the HC3 OH CH3Br molecule. So it's worth noting that the Grignard reactions act like carbanions, which means that this carbon is very nucleophilic. So the nucleophile in this reaction is going to be that carbon atom that's attached to the MgBr functional group. It's also worth noting that the epoxide is a very strong electrophile because this three molecule ring structure is very strained, which means that the bonds are very polarized. Consequently, they're going to be very eager to gain electrons and to balance out these bonds. So those are the electrophiles and nucleophiles for this reaction. The epoxide is the electrophile, and the nucleophile is that carbon atom. Is that carbon atom attached to the MgBr. So the overall electron flow, as we can see here, is that firstly, step one of this reaction, now this reaction undergoes two key steps. Step one of this reaction is that this nucleophilic carbon is going to donate a pair of electrons to the electrophilic epoxide carbon. And when that happens, we're going to see a bond form at that carbon right here. The carbon right here. Between the MgBr here, which is going to disappear, and the carbon here. So that we're going to be left with CH3, CH, CH2 attached to that carbon atom. And then that bond on the other bond on the CH2 is going to be broken, and those electrons are going to flow up to the oxygen atom. So we're going to be left with an O minus attached to that group over here, attached to the MgBr. And we're going to get this intermediate molecule. From here, it's going to undergo a neutralization reaction. So basically, we're going to be working to remove the negative charge on that oxygen atom. And we're going to do that by using H3O plus. So for this purpose of this reaction, these electrons are going to flow to one of the hydrogen atoms on this H3O plus, and it's basically just going to grab one of the hydrogens, or grab a proton. And how that's going to work, I didn't write this down before. How that's going to work is we're going to have O, H, 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 and an electron pair, which is going to be causing this positive charge. The lack of an extra electron lone pair is going to be causing the positive charge. And what's basically going to happen is that this electron pair is going to grab a hydrogen, and then the hydrogen, the electron pair that's here is going to be redonated to that oxygen and flow back. So we're going to end up with H2O as a byproduct of this reaction. The final overall product is going to be H3C, and we see this right here. H3C, CH, CH2, CH2, CH with an alcohol, an OH group, CH2, CHC, and then these two groups on the ends here. So that's going to be the overall final product of this reaction as we see up here and as was provided in the PDF. So it's worth noting two key things. Firstly, the regiochemical preferences of this reaction, of the molecules involved in this reaction. So notably, we see there are 2 carbon atoms apart of this epoxide group, and the nucleophile is going to attack the less substituted epoxide carbon. So this is basically because undergoing this, there's going to be less steric hindrance. And this group is going to attach to the carbon where it has like the less amount of bonds that it has to break, basically. And stereochemically, it's also worth noting that the epoxide is going to approach through the back of the bond up here. It's going to approach through the back of the OH bond, not the front. And it's going to end up in a trans conformation or trans orientation between that oxygen and the carbon on the MGBR, attached to the MGBR or that nucleophile. It's going to cause inversion of the attacked carbon. Sorry. So in conclusion, overall, this is a reaction between a Grignard compound, or a Grignard compound, and an epoxide compound, which involves the attack of a nucleophile onto an epoxide group, and thus this ultimately causes the protonation of an alkoxide. Now this is the alkoxide that we see over here. So it causes the protonation of that, which gives us this final compound.